Okay, second lecture on analogies for acoustical, mechanical, and electrical domain. And just to introduce, look at this MEMS microphone, how complex this is system-wise. I don't know whether you can see, maybe I try it again. These MEMS microphones that fall to my hand here. This is the device's 2006 timeframe. It's too small to show in here. You will have a chance maybe later on to see them in real. It's transducer from mechanical devices. It's an ASIC, interconnects in between the assembly on a small PCB, which gets a lid out of metal and a sound port. And we see already that all this covers mechanical domain, acoustical domain, then transduction again to a mechanical system into electrics, and finally to the output nodes. And to simulate this is, of course, an issue if you look at the dimensions, so bridging hundreds of nanometers for tiny diaphragms up to housing, and the housing is also acoustically active. So this is not straightforward. You need to find the right way to do so. And I know a lot of young students that are familiar with field finite element analysis methods that go on such a system with just discretizing and doing FEM simulations. This is certainly something which is difficult due to the scales that we see. Classically, you start with some differential equations to solve the situation of motion and fluidic situation, as we discussed last times with the Euler equation. This helps to get started and is maybe valid as long as the system is not too complex. So what I propose in this lecture is using circuit simulators and do the representation of the individual physical elements in your device with analogies from mechanical to acoustical and electrical laws. So the fundamental equation, you know, the ohmic law, for example, it is describing the losses in electrical circuits. Fluidic losses could be described with a similar equation. So this is something which is quite popular and very helpful in terms of acoustical simulation. And if you translate your acoustic or mechanical acoustical device into this formulation, you can use quite major circuit simulators that are fast in solving complex equations or networks. And then it's very easy to parameterize devices, and geometries are under consideration. So it's major, and yes, it is possible. We call these lumped elements, so they describe or are representatives for a bigger association of holes. For example, they are concentrated elements, and they are valid since the wavelengths that we are dealing with is typically much larger than the dimension of our device. As a reminder again, 3.4 millimeter is the wavelength of a 10 kilohertz tone, and this just starting to get into the dimensions of the housing of the microphone. So still somehow valid. And we have to keep in mind that we can describe only linear equations in this formulation. So whenever it is getting nonlinear or large signals, then we come to the limits, but we are on the sensor side. Sensors deal typically with small deflections, small signals, and this is a quite good situation. Now, I explain how this is going to work. On this slide, we have passive mechanical elements. We have a mass, we have a spring, and we have a damping element. Typically, the force, the kinetic energy is described with the law of mass times acceleration. So the first derivative over the velocity over the time. Very, very simple kinetic energy formulation. If we have a spring, we can describe this with a potential energy using the spring constant, or what we rather use in the acoustics, and therefore I put it for the mechanics as well, is a compliance. So the inverse of the spring constant is a mechanical compliance. So we can use this also, integrating the velocity of the spring, or simply having a relation for the dilatation of the spring. And last but not least, as I said, energy loss, like the Ohmic law, you have a force into a resistor times the velocity. So this is very simple equations, and we put similar equations on the electrical side for magnetic energy, electrical energy, and energy loss. And if we simply look at the formulation of the equation, force times mass derived over time of the velocity, and we compare this with the voltage into a magnetic coil, with the inductance somehow related to a mass, and instead of velocity, we are looking at current flow and the change of current over time. And we find this analogy in all these equations. And then we simply use this to translate the mechanics into into an electrical formulation. So we can describe the mechanics if we use those analogies. Force is analog to the voltage in a circuit, and velocity proportional to current. And we call this the first electromechanical analogy, force voltage analogy. And this helps us finally to describe circuits or mechanical circuits and solve them in electrical domain. Yeah, of course, if you look at the equations a little bit deeper, you could also do simply correlations between force and current, and you find again a similar description of formulas. While, for example, you don't look at the resistance, but the inverse, the conductance for the energy loss domain. So this is an inverted analogy. We call this the second electromechanical analogy, or force current analogy. And this is valid as well. And whenever you do such a transduction of mechanics into electrics, you have to be very strict in using the one or the other analogy, not to mix it, because then everything gets wrong. And we will discuss which of the analogies are meaningful in which situation. But okay, I see this. Maybe you have got this also from other lectures. We will use this intensively to describe the physics and the working principle of acoustical transducers here. So this is the whole table of comparison of the analogies. We have the mechanics domain in the middle. On the left-hand side, the first analogy, force, voltage, and on the right-hand side, the second analogy. And you can describe here the analogies, the elements compared to each other. Of course, you can give an impedance in the acoustics domain, in the electrical domain, and the admittance as the inverse in the second analogy. And then you'll be able to describe kinetic and potential energy as well as power. So this is simply a translation table to keep in mind if you get started. Later on, it's getting more easy. Yes, and what about these acoustical impedances? So we try to formulate the relation and the way of the impedances. We start with a mechanical impedance, which is the relation of force over velocity. This is how we define an impedance in the mechanics. So you have the dimension Newton seconds per meter. Then typically we have a specific acoustic impedance. So this is related already to the area that a force acts on. So this is simply a mechanical impedance over the area. If you have pressure or something, maybe you want to use this, and then we end up with Newton seconds per meters cube. And also the characteristic impedance that we had in the last lecture as well for air, and we discussed it also for fluidics and solids, is defined as pressure over voltage, or the density of air at normal conditions times the velocity of air at normal conditions. This again gives the 412 Newton seconds per meters cube. This is like the characteristic impedance, which we always have if we emit sound against free space, or if we receive any signals, then free space has this impedance. And if you transfer any energy, you are dealing with this impedance, of course. And then we come to the acoustic impedance. This is not related to the area, but related to the flux, which is surpassing this area. So flux is velocity times the area. Here, meters cube per second is the dimensions. So it's like a volume, which is rated over a time. And then we get this weird dimension, Newton seconds per meters to the fifth. So we see already we have three different impedance definitions, from mechanics to specific to acoustics, which are only related by the area. So if you start doing modeling, also in the lumped element situation or with analytics, and you collect equations from literature, for example, say microphone, speaker, whatsoever you want to design, and then you are looking for a specific calculation, be very careful, because very often specific and acoustic impedances are mixed in there, and if you not calculate your dimensions, you can be quite wrong, because it's always area or dimension squared, which is then wrong, and you get messy situations in your early calculations. So best is you always use the dimension as well in your calculation. That is a check mark, but this is quite usual. Let's have a look into ideal passive acoustical elements. First of all, a resistance. What could be a resistance in acoustics? Of course, if speech is or acoustics is surpassing a narrow tube, then you have, of course, a fluidic resistance, a tiny and longer tube, or alternative, you have a mesh or a gasket or anything which you put in front of your system, then you have also kind of acoustic resistance. Acoustical resistances is not so easy to describe, because this is fluidic loss. A very simple description for an acoustic resistance is here given with mechanical resistance divided by area squared. And for a fluidic tube of a length L, you have a quite simple formulation, this 8p eta being the viscosity of air times the length divided by area squared. This is true typically for systems below wavelengths, or for this kind of condition. And then typically for acoustic situation, you can simply use this, whether the tubes are micrometers in diameter or millimeters in diameter, it typically holds in those simulations. Of course, how to achieve this is a special calculation. We will see this later, the derivative of those fluidic losses. So how is this with the acoustic compliances? We can also say acoustical spring. So what is an acoustical spring? It could be a volume of gas, again, small against wavelengths. And you can compress this volume, of course, without acceleration, so constant compression and smaller displacement for the center of gravity. That means we have small actuation on such a cylindric volume, for example. And you can imagine, okay, you start compressing, it gets a pressure. We saw this before, this adiabatic or isothermal compression. This is giving a restoring force, which is acting like a spring. And for this, we can compare this with the electrical capacitors, which is also storing energy. In this terms, it is electrical energy. And the pressure inside is the force divided by the area that is acting on. And finally, we get here again the formulation in acoustical domain, flux time divided by frequency omega, J omega compliance. So from this formulation simply, you find again that the acoustical impedance is equal to the mechanical, acoustical compliance equal to the mechanical compliance times area squared. No wonder, it's the volume divided by density and speed of sound. Yes, meters cubed per Pascal typically is a dimension that we have here, or meters to the fifth by Newton. So this is an acoustical compliance, quite important in most of acoustical situations, and we see some examples for this. So we have the resistor, we have the compliance, and now we have the acoustical mass. Of course, a mass is a mass, also it is the mass of air, which is working on, and simply we can see that it is the acoustical mass finally is the mechanical mass divided by the area squared, density times the length of such a tube divided by its area. So this is the mass which will be accelerated due to any acoustical actuation. This is an ideal mass, so we don't check for the compression and friction inside this cylinder. And of course, we have always harmonic excitation in our mind and steady state, so everything is stabilized. And then we use in the first analogy an inductor to describe this. So this situation of the mass is special. If we have a tube with some openings at the front and back, and we accelerate the mass inside, we can see that there's of course something which we call the flange situation. So we need to add a little bit of the mass that is accelerated at the input and output of a tube, because this is somehow loaded to a tube. And this is a bit heuristical approach, but what people tend to do, they extend the length of the tube by a correction factor, delta L, to account for the mass which is loaded to the tube at the input and output. And then you find different studies about this correction factor, which is always in relation to the radius of the tube and is given between 60%, 80% of the radius of a tube. That depends a little bit on how you calculate this. And for this reason, you can simply extend a tube where you say this is a mass by an extension. And you can imagine these extensions, which is in the area of the radius of the device, get interesting the shorter the tube is. So finally, if you had not a tube, but only maybe a hole in a wall, this could be described mass-wise with nearly only these extension formulas. And this is coming from the times that you did not do fluidic computational simulations. Nowadays, you start to adding those from FEM simulation, CFD simulation, and you get an expression for this effective mass of a typical tube. Usually, it is not necessary to do so because it's coming again in the order of this magnitude. Yes, okay. Then we have all those three passive elements. And with those three passive elements, you nearly describe all acoustical micromechanical devices. And that we're going to do in one of the later sessions. What I can show you here is maybe some simple examples. Yeah. Oh, yeah. I got another impedance, which is very often referred to. It's the so-called radiation impedance. And this is a complex impedance and not too easy to derive. The issue is typically you have a speaker, it can be a big speaker, and can also be a microphone, and you have a vibrating element in. So as I said, in the free space, you have Z0, the correct specific acoustical impedance, and here you have the mechanical impedance of a driving element. Now you want to know how the energy is transmitted into free space from this vibrating cylinder. And to calculate this, we have here the expression of the pressure that this vibrating piston is radiating into space. So first of all, you integrate over the pressure that you have at the point in space over the radius. So you integrate over all this area of the emitting or receiving piston, vibrating piston. And from each of those points, P of R, you integrate then into space, into a segment of a semisphere in a certain distance of your point of integration into space. And this gives you finally the expression for the impedance. So the solution of this equation deals with Bessel and Struve functions. You can read this and you can compute this nowadays more easily. But typically, these solutions are given in textbooks and are simplified for easier use in applications. And we get here the complex radiation impedance plotted in relation of the radius by the typical wavelength. So if we have this x scale on 1, then we say the wavelength is equal to the 2pa to the circumference of your device. So if you get into typical wavelength dimensions. Since we are on the MEMS side, we typically deal on the left-hand side of this formulation. And on the left-hand side of the formulation, for the factor Ka below 0.5 is quite safe. Then we have more or less homogeneous development of those impedances, especially the ohmic or the loss part of it is going with the square of the frequency. So this is this formula. We see a very steep increase of this radiation impedance over the frequency. So if you're gonna model this and you have something which is radiating into space, you need at least to have a formulation which is frequency dependent. I can tell you already that typical solvers like SPICE, circuit simulators, they don't allow frequency dependent passive elements. Then you check on which level this impedance is it relevant or is it not relevant? And maybe you neglect then radiation impedance, or you have to find different solutions. The other part of the impedance is the mass, acoustical mass, which is of course proportional to the diameter of your size system. And this is also relevant typically for large devices. So the acoustical mass is of course an issue. And what we see then on the high frequency side, or whenever we have very large, when we have very large devices, then we come close to the characteristic impedance. Then we have the loss term equal to Z0, 412 Newton per meter cube. And then we can neglect or we stick to 1 normalized impedance Z0. Yeah, this is a situation that you can account for, and just to see what it means in terms of loss and acoustic mass. For a bass speaker, I have 10 centimeters, not a bass, it's 20 centimeter diameter. Okay, typically 250 hertz, such a speaker is resonating at. And that means we are just in the middle of this curve. We get a loss of 1.2 Newton seconds per meters cube, and is a load of 76 grams per meter square. So we feel already the weight or the impedance of the air in such a system. So we cannot neglect this radiation impedance. But if we look to a MEMS microphone, which has only a millimeter diameter, so 1 millimeter radius, and maybe at 10 kilohertz, yeah, then we can find some loss factor which is not too far away from a big speaker, but the mass loading is of course much smaller, 0.8 gram per meters square. So meter square is of course not a good relation, but you finally have to check whether this mass is relevant with respect to the physical mass of your tiny diaphragm. And since the diaphragm is also only 100 nanometer thin, you have to check this finally. So this is radiation impedance, and there's different solutions that you can find for different situations, whether you have a square or a cylindric or whatever radiator or a receiver. Good. Okay, this is a special case of impedance, and we see how complex it can be to solve this. That is passive impedances, and of course we have also ideal sources. So we describe, of course, the source like a sound source with different analogies. We can express this in the first analogy or in the second analogy. Both can be translated into each other. So in the first analogy, we have a pressure source which is generating a flux. And yeah, if you look at this symbol, this is like equivalent to a voltage source. It has zero source impedance. While if you had a constant volume flow generator, it's like a current source, it has infinite source impedance. This is the inverse, the second situation. Most often we stick to pressure sources. If you use a pressure source in the second analogy, of course, then you are generating pressure from this pressure source, and the potential energy is a flux. And of course, then you have an infinite source impedance. Okay, most often we deal with these pressure sources equivalent to a voltage source in a circuit description. Yes, okay. Domain, let's, I don't know whether this is the right order of, yeah, okay. I get you some example about acoustical circuit. Yeah. A very, very simple one, usually people know the Helmholtz resonator, which can be a bottle with a flange and a volume behind. So this the bottle situation. If you have air streaming along this, the mass in the flange is getting into, is getting accelerated, is getting into resonance maybe. Everybody knows that's generating tones, and the mass is accelerated or vibrating against this volume inside. This is our acoustical compliance. So if you have this situation, we can simply explain this in the first analogy with a pressure source, which is the outside pressure source of air, which is blowing against this, or which is vibrating source. We have the mass of the flange, which is an inductance here in the first analogy, and the compliance is given as a condensator. Yeah, and this is a resonating circuit, and the resonance frequency can be derived typically in simple formulation of LC situation. And if we transvert this back into the acoustical domain, we can use MA and CA instead of L and C in the electric domain. So we have the resonance frequency in this formulation here for the acoustics. And of course, we can now use the acoustical mass, which is the length of this tube here, times 2 times in correction for the flange opening. Yeah, this is 2 times 64% of the radius of this flange divided by the area squared. And the compliance is simply the volume expressed in acoustical domain. And then we get expression for the resonance frequency of this system. And okay, this is the macroscopic explanation or representative with this bottle situation. If you look at a MEMS microphone, the same that we saw before, I put here the cross-sectional dimensions. As I said, is around about 4 by 3 millimeters in size and height of about 1 millimeter. this gives a volume of 8 millimeters cube. And this port here, this little hole in this metallic lid, is 0.8 millimeters in diameter and is only 200 micrometer thick. So it's a tiny hole. And if you have such a hole together with this volume, you can expect special resonance. I checked up if I use this formulation into this formula, and you see from the 0.2 millimeters and the 0.42 radius, this flange formulation is a stronger impact on the mass than the tube itself, because a wide and short tube. So from the calculation, we get 70 kilohertz resonance frequency. And I checked the data sheet for this special device. I could find data sheet only up to 10 kilohertz. But you see here's the relative sensitivity of my device is flat over the whole frequency band, and at higher frequencies starting to increase. And I know that it's developing somehow a resonance before 20 kilohertz. That I don't have calculation for this or a measurement for this, I'm sorry. I checked recently on the web whether I see this again. No, I don't have this. Yeah, here I have a data sheet of a microphone with a different configuration, I have to say. Configuration is such that not the hole is in the cap, but it is below the microphone. So you have a hole below the microphone chip and working with the chip as a volume. And I checked up again. Here you see 20 kilohertz is developing a resonance or higher sensitivity is the normalized output signal of the microphone. And then they extend the measurement up into the ultrasonic range. And there's 20 kilohertz, there's 40 kilohertz, and in between 20 and 40 kilohertz, it is developing this resonance. And this resonance is exactly the Helmholtz resonance of the package. And since the hole is smaller and the volume is also smaller, the frequency is shifted to higher frequencies. And from this, we see already Helmholtz equation is important to engineer the package of a microphone, because we don't want to have a resonance before 20 kilohertz, because this is still human hearing range. And if you have a resonance at 14 kilohertz, is like you display classical music or anything, it is not nice to hear that special frequencies are overpronounced, and this would be very nasty in listening. This is an early device. Those times specs is anyhow only up to 2, 3, 4 kilohertz. This is the specification range for telephony. And beyond is not too important. Maybe electronics is band cutting this audio, this special telephone bandwidth. Okay, this is simple lumped elements for Helmholtz into MEMS. Okay, we have been dealing with this acoustic compliance. And there is a rule in acoustics that whatever is acting, fluidic losses together with accelerated masses, is always acting on a wall, so to say. Yeah, it is connected fluidically to each other, and we describe the wall in the housing or wherever as the ground potential in the electric domain. And those compliances, which take the energy and store it as a compressed air, they have always a wall behind which it is resting on. So whenever you find circuit simulations or circuit descriptions where you find acoustical compliance between two other impedances in series, there is a mistake in setting up those networks, because the compliance always has to go to ground. So you cannot have a resistor and a compliance in the resistor. If I find something like this in the acoustical lumped element network, you need to check it and ask people what they did in here. Most probably there was a wrong situation. Later on, we will see how we bring together networks, and such situation are allowed, but not for acoustical compliances. We can translate mechanical compliances into acoustical networks and represent mechanical spring in series with acoustical elements, but then it is not an acoustical one. So keep in mind, any capacitor in first analogy has to be grounded. Yes, we had another simple explanation or example about acoustic resonant circuits. Absorbers. You know, how do absorber work? You know those ceilings. You have holes in the wall to absorb acoustics. And how is this absorber working? It is nothing else but, again, kind of a Helmholtzian situation. You have a plate with holes inside, and is just an array of holes. Okay, yeah, it's not a single one, but multiple holes. And of course, you can calculate the mass of all those holes together, here described in the area of a plate and the density of holes. We don't add all the holes, but we give it a density like 25% of holes in such a plate. Then we have this typical situation. Of course, there's a typical length of the hole and radius of the hole if it is circular. And this gives you the total mass, which is excited against the volume behind this plate. So those absorbers work only with a cavity behind them. And this giving, again, the compliance here calculated again from this acoustical compliance. And both together give you the resonance frequency. And now the question is, how does it help to filter the situation, or help to improve the acoustics of a room? If you look at the data sheet of, this is from Knauf, they are selling these regips plates with the holes inside that will be installed in rooms. They have a 20% of density of holes with something like 12 millimeter thickness and 50 millimeters diameter. And you can simply use this equation and check for those dimensions the resonance frequency. I did so 260 to 640 hertz. And this is the data sheet measurements of the absorbance of those plates is fitting somehow. And we see this is typical resonances of speech, or frequency of speech, which is in the band 250 to 123 kilohertz. And we try then to absorb the energy which is impinging on the wall into those resonators. And finally, this is like the sink of energy. It is absorbing energy exactly in the range of the resonance. And then is one important point you see here from the measurements, that is a not pronounced resonance, not a sharp resonance, not a high quality factor, but it's a very broad system. And for this reason, you need to put some damping material into your cavity. So you not only have a C compliance, but also a loss element inside. So this broadens then finally the resonance of the system, and allows to do a little bit broadband absorption into the room. Yeah. So if they do a damping in here, it's getting even wider. And this is what people do in room acoustics. It's so simple here, this example. But room acoustics is a subject on its own, quite complex, but not interesting to us, because this is just a macroscopic side of acoustics. Okay. So now we start putting mechanical elements into circuits. I have here a simple situation of resonating mass, which is accelerated by an external force. And of course, we have a damping element and spring element in series parallel to it. So the forces, I always have to correct myself, they act in parallel to each other. and then you can add the forces. So this is clear from the force diagram how to add up force vectors. Now, if you describe this in the first analogy, you simply say, so I add up the forces, which is the analogy in my network, I add up the voltages. So this looks like intuitive, therefore very often such circuits are simply described into this impedance true force voltage analogy. Of course, you describe it in the second analogy, same, but then you end up with parallel circuits. And the description or the solution will be the same, just you have used a different implementation. But of course, if we want to have a simple expression of the impedance, we're doing much easier with the first analogy in this situation and can solve from there and again find our resonance frequency and a quality factor of this resonant device, where we see that the loss elements are dominating. So this is the simple circuit for parallel resonant circuit. Of course, we have also a serial resonance where you have the force and velocity description in series. So you can add up the velocities, not the forces in this situation. And this is a different case. So if you have this situation of a mechanical expression, you easier jump into the circuit description with second analogy, because then you simply add the velocities, or now the voltages are equal to the currents, and you simply go for this, derive here your impedance description and all the parameters that you want to have from this resonant circuit. So it's the easy way. Typically, you never have such simple formulation of networks, and yeah, you have to always, if you solve it by hand, Kirchhoffian rules you have to obey and do it by hand manually. On simple solution, this is also interesting to do so. I give here a very general description how you can transfer a circuit that is given to you in the second analogy. Since those analogies are yeah, how should I say, they are equivalent. So you have your transduction law and the inverse topology of the circuits. You can try to simply redraw your circuitry that you get. In this case, we start with admittance type, where we have the second analogy. So masses are represented by condensers, and the admittance is given by an inductor. You want to have this in the first analogy. Sometimes it's easier to deal with. So there's a simple rule that if you want to do so graphically simply, you put in dots for each of the meshes. So this is the meshes here in the circuit diagram, one outside. So then you have to define all those meshes, and these mesh numbers are later the nodes of the inverse circuitry in the impedance situation. Secondly, you simply draw lines which are going through all the passive or active elements and each one of those nodes. And you see this is these two lines, and these lines are now already the representation of the new network. And then you can draw this, or you simply draw again, then we rephrase it. One is here, and 1, 2, 3 is connected to each other, 1, 2, 3, and coming back again. So we have now the same loop as here, and the other one as well. So with these loops, you know now the topology of the circuitry. Now finally only have to do the dual description of your elements. So M2 as a capacitance here is an inductance now, M2. the conductance of the resistance here, G1, is now a resistance band. And yeah, this is simply the situation. And now this looks not complicated. If you have a little more complicated microacoustical situations, maybe it is meaningful to use this algorithm simply to transfer between those situations. Okay, this is simple stuff. And last but not least, it is important that you be able to formulate complexer situations. Yeah? We have to transfer between different domains of energy. So we have acoustical, mechanical, and electrical domains. So if you want to solve it, we need to translate it finally into the electrical domain. And how this can be done is described in transformation networks. So to say, I have to switch this. I'm missing some slides. No, here they are. Sorry. Yeah. You want to transform between those domains, and finally, if you do so, you'll be able to connect those domains. But the connection of the different elements is important, and it needs special systematic of two-port or four-pole networks that can stagger then finally together. And we have simply mechanical acoustical transducers. On the one hand side, we have force times is equal area times pressure, and on the acoustical domain we have the flux equal area times the voltage. And if we want to describe this in electrical representation, we have an acoustical mechanical side in admittance type on acoustical side in admittance type. So we are admittance true here, and we simply use ideal transformers. It's like a coil-coil system, and the winding relation is simply the area. So if you formulate your mechanic circle on this side and the acoustic circuit on that side, and you put this relation in, then you can solve it in one and the same circuitry. You can do this on impedance as well. So we have velocity transferred into flux and force transferred into pressure, as we had it very often. So those elements are available also in circuit simulators if for some reason you don't want to transfer the elements into the other domain. So you connect the different domains to each other. This finally, we will see this later in simulations, gets clarity which elements are in the acoustic domain, which one in the mechanical domain, and gets clarity in your system. And then you can simply read it as if it was a formula that you put together. So there's also a simple explanation how you can do this for magnetic mechanical transducer, like a loudspeaker. We have voltage generated by a moved coil or inductor in a magnetic field, or we do it inverse. We have a current through a coil generating a force when the magnetic field develops in here. And we can transform from the electrical into the mechanical side simply by the winding situation, B field times the length of the coil, or the number of windings times the length of the coil. And this is simply the relation between these two domains, because then you can have a closed description of your electromagnetic transducer. Again, here you can read it like a formula. Yeah, always keep in mind that you use ideal transformers in those systematic, so you don't get bandwidth limitations or anything. This is a very simple situation on such an electrodynamic transformer, and I choose this headset. Headsets are very popular nowadays, and this is a description of an electrical element on the left-hand side with a voltage driving a coil. This is now the coil of this speaker with an inner impedance or loss, 8 ohms typically. You drive it with maybe something like 1 volt RMS. And on the mechanical side here, we see here the admittance type of circuitry. We see that there's generated a force with this transduction here, and the force goes into the mass of the diaphragm. So it is accelerating the mass of the diaphragm of this speaklet, and the other force goes into the impedance of the ear, here described as a spring. So we see here the mass of the accelerated mass of the diaphragm sees the spring of the air volume in the ear channel. This is a cross section to an ear, for example. And this eventually, this is a very simple description of an earphone. And the question is, what the sound pressure level that is generated in such a situation is very simple. We have also mass of the diaphragm given with the length of the inductor of the coil, which is wound around the speaklet. The magnet is 1 Tesla. And we get the impedance of a typical hearing channel, this complex given in this acoustical domain, in this admittance type here. Yeah, to solve this, of course, we can put this in the circuit simulator, and we have immediately a solution. If you want to do it by hand, you better transfer into one domain, and this just inverse what I was talking before. We transfer in this special case the electrical domain into the admittance type of mechanical formulation, and can then derive from there simple formulation of the circuitry. We transfer the voltage into the electromechanical transducer into a mechanical velocity just by using this transformation factor B times L over 1. Yeah, and we can do so. It's a little bit strange that we have BL squared in the denominator for the resistor, which is transferred now into the mechanical admittance type, which is due to the mechanical admittance and the transformation. You can read this in the former slides. Now we see we have everything in one domain in the admittance, mechanical admittance type formulated. And then from the Kirchhoff's laws, we can have these two meshes, and we simply can calculate this down and find then that the absolute pressure, the level of pressure that we are developing here is ending up in 169 pascals. If we use then the 169 pascal, we refer it to the 20 micropascal, take the logarithm times 20, we get the sound pressure level out of this. And this simple example gets us a sound pressure level of 139 decibels. It's crazy loud, so this would be a dangerous headset. But it simply should describe how we get from the electric and magnetic transduction into an acoustical sound pressure level. And yeah, this is how it can be designed. The inverse is true as well, but it's very straightforward. Again, we simply look at a speaker. Okay, we neglect at this point the radiation impedance. We simply say we have a certain impedance, which the speaker is driving typically. So this speaker sees a load of 40,000 Newton seconds per meters to the fifth if you drive it with 1 volt RMS. So this is similar to a 2 watt of acoustical power out of this. So 100 square centimeters is not too big as a speaker, but is a typical smaller speaker. And the question is, if we use this as a sensor, so we have a sound field working with an RMS velocity of 10 centimeters per second. This typically, if I speak here to such a speaker and I put a voltage read on the other side, can this work as a microphone? Yes, it can. Simply, you use the formulas of acoustical and mechanical impedance here that is given here, and the force out of electromagnetic transduction of this system. Then finally we get from the power formulation again the situation that we have an RMS voltage at the clamps of the speaker of some 140 milliwatts for this special sound. This looks like a comfortable signal, and I'm sure you could really use this for a microphone, but the micro is already wrong here. It is detecting acoustics, but nobody is really using speaker for sound recording. But okay, could be done. Yeah, now I have a very special transducer in the acoustics. We are dealing with pipes of different cross section. We will see later in the packaging. Similar like the holes in the microphone, there's a bigger one and a smaller one, or the housing to the microphone with a longer tube. You can imagine that you always deal with tubes where the sound has to pass through. Yeah, on one hand side outside, and the other side maybe the microphone. And the question is, what does this mean? Now, since we are in the acoustics, we know that in both of the tubes we have the same pressure. And we know also that the flux is the same. So the flux is velocity divided by area. So this will be constant. Yeah, whether it's a smaller device, then I have a higher velocity, but a smaller area. And here the velocity is smaller, but the area, here high velocity and small area, low velocity and large area. So the flux is the same, the ratio of it is the same. This means the acoustical impedances are unchanged, that Z1 is equal to Z2. And this is looks strange, but it is true. So you don't need to have an acoustical transformer. But if you describe this in mechanical domain, then you have to use a transformer in between. So because now the velocity is changing and the area is changing, then you need this simple transduction. Maybe this is also a reason acoustic engineers like the acoustic domain to describe systems. Yes, okay, now we have all passive and different lumped elements to bring together. And we had already this transformation from first into second analogy of circuits. There's a different way of formulating this transmission of energy, and this is simply the two-port network idea that we try to formulate our networks with. And assume we have a network with an input and an output, and we don't know exactly what is inside, but we can formulate this as a two-port or four-pole description, where we have, for example, a source at the input and a load on the output. And the simple formulation is done with this A matrix or transmission matrix. So we have input parameters on the left-hand side, output parameters on the right-hand side, and the transmission matrix is, is in between. So this transmission matrix can easily be given with A11 to A22 parameters. And we can solve this without knowing what is really inside. So this is sometimes helpful if you have a network, maybe in the RF domain or in the acoustical domain, I don't care, and you want to test this. And you can get a full description of those parameters in the matrix by testing. So for example, A11 is the ratio of input voltage by output voltage if output current is 0. Output current 0 here you get if you have an open. You simply keep it open and then you do the test, measure the output voltage, the input voltage, and you get A11. The second parameter to test in the matrix A12, relation of input voltage by output current in case that the output voltage is 0. If you set output voltage 0 and you solve this, you get this simple information. Output 0 is shorted, so you short the output of your network, measure current and input voltage, then you get this parameter, and so on. You can get all those 4 parameters, and that you get the full description of your network. Popular to do so in network theory, and the nice thing with this situation is you can multiply those matrices, so you can subdivide your network if it is complex into different subnetworks, test them if you want, and then connect however you want, and you can use this. The same is true for impedance matrix, so you can transfer between impedance matrix and transmission matrix. The benefit of the of the impedance matrix is that you have a formulation in the voltage on the one hand side and the currents on the other hand side. So it depends how you want to solve your network. You use either Z or A matrix. Now this is very academic or top level. If you have typical acoustical networks that you want to solve this way, this is just an example for an electromagnetic intermechanical transducer. So a speaker, for example, or a motor, electromagnetic motor maybe. So typically you have an electric driving voltage over an impedance into a coil. So this is the coil side, and on the force side you develop a velocity, maybe a motor or a voice coil or whatsoever, into a load, internal load and external load, which is developed and then finally a force into an actuator, for example. And then simply you put for each of these subsets the matrix, which you can simply derive from this simple equations. They repeat always, and then you get a formulation that you can simply solve in MATLAB or something else. Yeah, and yeah, this finally gives you a complete description of your transducer. And there's another one, electrostatic intermechanical transducer. Yeah, here D31 is for a piezoelectric device by the compliance of the piezoelectric transducer. You see here on the input side the capacity of the piezoelectric device, on the output side again a load situation. So this is a quite easy way to describe systems alternative to the circuit simulations, yeah, just to complete the way of formulating solutions for acoustical multi-domain systems. Okay, yeah, this is maybe wrapping up for today. Yeah, try to get you an idea about this multi-physical domain description of acoustical devices, give you insight into the passive mechanical elements and electrical analogy. Very often we will use the force voltage analogy later on in the description of a microphone. To do so, we use the acoustic impedances, which is pressure over flux, or mechanical impedance over area squared. And as said, we have a dimension of Newton-seconds per meters to the 5th. Yeah, with ideal electrical transformers, we can even bridge between the different domains and do a joint simulation in a circuit simulator. And alternatively, we can solve those networks by transmission matrix concepts in terms of two-port networks. Yes, this is what we could share today. Oh, yeah. I was sorry. I thought I have again. I was